Okay, welcome back once again. This is the beginning of Module 5. We're going to describe the physical and chemical assessments for IDAH2O. Now, these next assessments really are a combination of two. The physical assessment includes observation of physical characteristics of a stream. These characteristics influence the chemical and biological aspects of the stream. You can follow along in the handbook. You will find the physical assessment techniques described on pages 29 to 34 and the chemical assessment techniques described on pages 37 to 41. These two assessments are combined on one data collection form found on pages 35 and 36 of the handbook, or downloadable from this module, or downloadable from the IDAH2O website. You will use this form to document all of your observations. Remember that you'll need to monitor your monitor number, a site description, information about others who monitor with you, that metadata. If you check on the online form, stream unsafe or too dry to perform all measurements, the form no longer requires all data points to be entered before you submit the form. Now, a few other things to remember about the physical and chemical assessments. First, your readings are affected by the time of day and weather conditions. To improve consistency, it's best to take your measurements about the same time of day. It's okay to take measurements at different times, but a greater discrepancy from the previous readings may result. You can include a written note at the end of the form if you monitor at a time different from your normal monitoring events. You can download this flowchart here at the bottom left from this module. It's a great demonstration of the interconnectedness of many physical and chemical stream characteristics. The first data you will collect in this assessment is to describe the weather. The weather affects many physical and chemical characteristics of the stream. Warmer air will result in warmer water, in turn reducing the dissolved oxygen concentrations. Rainfall can increase non-point source pollutants and decrease the concentration of point source pollutants. Use your senses to gather data about some water quality parameters. Water color can tell us a lot about pollution problems. Brown water likely contains a lot of silt runoff from erosion. Green water is indicative of some sort of bloom of microscopic algae or cyanobacteria. That multicolored sheen on the surface of the water can mean two things, both related to oils of some sort. Now, if you poke at the sheen with a stick and it breaks apart and doesn't swirl back together again right away, it is quite possible that oils from the natural plant breakdown is occurring, and that's what's in this picture here. If it does swirl right back together, it is likely some sort of petroleum product like oil or gas. Now, reddish water can be caused by some types of soil or some types of red algae blooms. Blackish water can be caused by raw sewage. Some water that is dark in color but also clear like tea contains natural tannins from swamp vegetation. A lot of rivers in the southeast US are this dark tea color, and that's perfectly natural. Milky water often indicates very fine particles that are glacial in origin. Water that runs gray can indicate a number of pollutants from fine mine tailings to dyes used in the manufacture of apparel and other products. Note the color on the assessment form, or if it's clear. The odor of the water itself, not the air around it, can also tell us a lot about the quality of the water. Manure or sewage smell can be from overflowing septic tanks, wastewater treatment plants, or animal manure. Rotten egg smell is indicative of low dissolved oxygen conditions, anaerobic processes, and unhealthy aerobic conditions. Fishy odors also indicate unhealthy aquatic life. Take a close sniff of the water itself and note whether it has a noticeable odor. Hopefully it doesn't. The clarity or transparency of the water is affected by fine sediments, especially silts and clays. It can also be affected by unicellular algae and plankton in the water. Transparency has a corollary measurement called turbidity. Turbidity refers to the cloudiness of the water. Turbidity is measured in units called NTUs and requires a more sophisticated meter and sonde or probe to quantify. Transparency of the water can affect a fish's ability to find food. and it can affect the sunlight reaching through the water column. More turbidity can also increase the amount of sun's energy absorbed by the water, increasing the temperature. We measure transparency because the measuring device is an inexpensive transparency tube or Secchi disc with a particular black and white pattern. In streams, we use a transparency tube, a 60 centimeter long clear tube with a small Secchi disc and a drain spout at the bottom. Here's what it looks like when you look down the tube. You carefully fill the tube with creek water and then look down through the column of water down the tube to see if the Secchi pattern is visible. Even if it is only barely visible, then your measurement is 60 centimeters or greater. If you cannot see the Secchi pattern, once the spout's valve is open, keep looking down through the water column until you can just barely see the pattern. At that point, stop emptying the tube and record the number of centimeters you can see through the water. In standing water, we use a Secchi disc. This is an 8-inch wide round weighted disc tied to a rope marked at 1 meter increments or a measuring tape. You lower the disc into the water on the side of the boat away from the sun and waves. You wait until you can't see it at all, and then you mark that depth on the rope. Maybe use a clothespin or something. Then raise it until you can just barely see it and mark that point. Find the midpoint between the depth at which you lost sight and the depth at which you regained sight of the disk. That's your Secchi disk depth reading. Ponds, being still water, will allow sediment to drop out of suspension more quickly. Therefore, a Secchi disk measuring in meters is a better instrument to measure the clarity than a transparency tube. Streams carry a lot more sediment since they have the energy to move sediment around. A transparency tube measuring in centimeters is sufficient for this measurement. The two primary chemical assessment data we collect is pH and dissolved oxygen concentration. pH refers to the acidity or basicness of the water. pH is measured on a scale from 1 to 14, with 7 being neutral. Readings lower than 7 are acidic, and readings above 7 are basic. Some people call that alkali. Water can naturally be slightly acidic or basic without being harmful. The normal range of stream and lake pH is between about 5.5 and 8.5. Distilled water will have a pH of 7, and many things can affect the acidity or basicness of water. Rainwater is naturally slightly acidic, about a pH of 5.5 to 6.0. Carbon dioxide dissolves into the rainwater, turning into carbonic acid, a weak acid. Bedrocks and soil can make the water fall on either side of neutral, though, too. Limestone can dissolve and form carbonate compounds, weak bases, and cause more basic water. We measured the outflow of Henry's Lake near Ashton, Idaho, in that rather volcanic district at a pH of 9, or very basic. Now, there were plenty of fish and aquatic macroinvertebrates there regardless. IDAH2O uses a particular type of pH test strips. These Hawk mid-range pH test strips are suitable for use in an unbuffered solution. Otherwise, these are very similar to the test strips or pH paper used in pools, aquariums, and science classrooms. Quickly dip the end of the strip with a thicker pad into the water and then immediately remove it. It doesn't need to sit in the water. Wait 15 seconds for the color to fully develop. At the 15-second mark, compare the color of the pad with the color comparator on the side of the pH test strip container. You will need to estimate the pH to the closest whole number. Remember to remove your sunglasses as that can affect your reading. Dissolved oxygen is essential for aquatic life. Some processes add oxygen to streams and others consume it. Oxygen does not dissolve all that readily, and so concentrations in water are far below those in the atmosphere. Concentrations are measured in parts per million, or milligrams per liter, because if measured in percentage, it would be an awkwardly small number. A wide variety of physical conditions can create huge changes in dissolved oxygen concentrations. Cold water is capable of holding more dissolved oxygen than warm water. Same goes with clear water and water with lower dissolved solids. On a sunny day, aquatic plants can produce a lot of dissolved oxygen, but the sunlight can warm the water, causing that dissolved oxygen to drop. Water flowing through riffles and increases in wind can increase dissolved oxygen. IDAH2O uses a dissolved oxygen test kit containing small glass ampules manufactured by Chemetrix. Each ampule is a sealed vacuum tube with a pointed tip and a weakened point on the tip. The tube contains a small amount of liquid that, when mixed with stream water, reacts with the dissolved oxygen in the water to turn blue. The darker the blue color, the more dissolved oxygen in the water. The kit also contains a small plastic cup with indentations on the bottom. So you fill the cup with stream water and immediately insert the tip of the ampule into one of those indentations, the one closest to you, and then pry the ampule back toward yourself in a way that breaks the tip off at the weakened point, using the curvature of the ampule and the side of the indentation. The ampule will immediately mostly fill with water and will start to turn blue. You need to wait exactly 2 minutes for the color to fully develop. At the 2-minute mark, compare the color in the ampule with the color comparator included in the kit. Record the reading marked on the comparator closest to the color in your ampule. Round the reading down to the lower reading on the comparator, even if you think the color is between two comparator tubes. You will get plenty of opportunity to practice this in the field, so don't worry if this description is a little difficult to follow. Our assessment form also includes a line for entry of chloride data. IDAH2O discontinued collecting chloride data because the test strips are somewhat expensive, and Idaho's water rarely have any measurable chloride concentrations using this technique. You are welcome to measure the chloride. I can get you information about the type of test strip to use, but you'll need to source the test strips yourself. This is not a mandatory field in which to enter the data on the online form. IDAH2O also does not measure nitrates or phosphorus. In the early years, we had the capacity to hold twice-yearly snapshot events where North Idaho Master Water Stewards could bring water samples to the University of Idaho Coeur d'Alene Center for more sophisticated analysis. The detection limitations of common nitrate and phosphorus test kits or strips are too high to measure the relatively low concentrations in most of Idaho's waters. We used a spectrometer and a titrated solution in the lab to measure these concentrations, and still our equipment's detection limits were frustratingly high. Finally, the water samples had to be processed within 6 to 8 hours of collection, so only North Idaho water monitoring sites were close enough to get the samples to our lab in time. Since IDAH2O has grown to cover most of Idaho, these snapshot events aren't really possible anymore. We have discontinued this service, but there are local private laboratories around our state that can do a better job of these very same testing, better than we ever could. I can help you locate and contact a lab in your region. The amount of water flowing down a stream can be measured with simple tools. Flow is a function of the width, depth, and velocity of the water. First, measure the width of the stream from the ordinary high water mark on the left bank to the right bank's high water mark. Then, use a meter stick to measure the depth at 1 meter increments out from the edge of the water. If the stream is 2 meters wide or less, just measure once in the middle. While you're at it, find the maximum stream depth and record that on a separate line on the form. You don't need to fill in every line of this portion of the assessment form if the stream is less than 10 meters wide. Or, if you'd like, divide the total stream width by 10 and calculate the depth at each of those increments across the stream. IDAH2O measures velocity, or how fast the water is moving, using a tennis ball tied to a 1 meter long string. Highly technologically advanced, right? Well, it works, believe it or not. With your scribe standing ready with a stopwatch, float the tennis ball and hold the other end of the string right with the ball. Be sure your body is not affecting the stream flow where the tennis ball is. Release the ball when the person with the stopwatch says go, but keep the other end of the string that you're holding between your fingers still. Allow the ball to float downstream until the string is taut. As soon as it's taut, stop the timer and record the number of seconds it took for the ball to float 1 meter. We suggest that you repeat this procedure at least once at each meter mark across the stream. I recommend repeating this 2 or 3 times at each location across the stream and then averaging the number of seconds at each location. Okay, that was pretty quick. The physical chemical assessment is the fastest assessment. Once you get used to it, it shouldn't take you too long to perform. Now that's the end of that module 2. So move on to the quiz for this module, and I'll see you at module 6, the biological assessment.